on a WebAssign. Yesterday, you had to answer 4 questions, number 1, number 2, number 3, and number 5. So 2 students answered 12. And they did it in the first 2 minutes of the class. So I don't advise doing that. Well, so far, no one was late, which is good. But more importantly, it works. Yeah, I always, sometimes, once in a while, something is happening and WebAssign just crashes. In that case, I need to know that. So I would have to take attendance the old-fashioned way, to pass around a piece of paper. I expect at least 2 more students should join the class today. So if you missed your lab, talk to me. I can give you an option to make it up. Motion, that's what we want to talk about today. And let's start from this question. Here you can see a system. Sometimes in the future I will ask you, what is a system? So you can start thinking now about it. A red object, a yellow, and a silver. And this is what I'm going to do. Can you remember that? I can repeat it, because looking for patterns in science, we need to be able to repeat the same experiment again and again, and see that every time we observe exactly the same processes. So the question is, that's not a WebAssign question, just to you. This guy, yellow one, was it moving or resting? Yes.
In reference to the red clock or general motion?
What do you think?
Yeah, it moved.
You think it was moving?
I think it moved relative to the one that was stationary.
What, gentleman in the middle, what do you think?
I think it
Can't hear you.
I think it moved.
It moved, yeah. Definitely. Oh, I mean, or definitely? Definitely. Okay. So every time in a situation like that, we may have variety of opinions, and in physics, this is simple experiment tells us in physics we can't answer this question without asking additional question, because the information is not enough. The answer depends on relative to what? In physics, motion is never absolute. It is always relative to a certain choice of a reference frame, of origin, reference point, and where can we choose the origin or the reference point? Where? What do you think? Someone said something. Where in the universe can we choose the origin, the reference point? Yes? Earth, where else? Well, you can name at least 7 more planets, right? If you follow this path. If you follow a different path, where else? Where else can we place it? Choose it. Starting position, or can we choose it on the sun? So can? Yeah. Yes, all right. Can we choose it, I don't know, on a North Pole? So? Anywhere. So the answer to this question is simple: anywhere. In physics, it's very important to have that flexibility, and we have to use that flexibility for our advantage. If we can choose it anywhere, we choose it there where we want it to make our reasoning as convenient as possible. And we can choose the origin in this situation here. Here, this object is my origin. So relative to this origin, the yellow object has been moving, right? And when I say origin, I should use my imagination. I imagine myself as a tiny person looking from this around the world. What is happening around me? So this yellow object is traveling away from me. Now I can choose the origin. Well, if my system is composed of 3 important objects, 1, 2, 3, where else can I choose it? Well, at the red one. So I have to, again, mentally place myself on the top of this object. Imagine I'm here, and I'm looking around, and what do I see? So relative to me sitting here, does it move? No. Does this move? Yes. Relative to me sitting here, this flies away, but this doesn't move relative to red. The distance doesn't change, orientation doesn't change. So this is a very important point. We have to keep in mind every time when we talk about any kind of motion, it is relative. And normally people do not even name the reference point because normally they assume that's the earth, that's the ground. But sometimes there might be exceptions, so just be careful. If you read a problem about airplane flying or ball falling, normally that's assumed relative to the ground. But we will be considering situations slightly different from that. Well, the motion. When something is moving, the location is changing, and we want to describe it, we need means to do that. One of the means is to take a photograph. Oops. Then another photograph. Then another photograph. Then another photograph. And eventually, we can place all those photographs together. And that picture tells us the location of that object at different times. When we start the stopwatch, that's what we call t equals 0. Yeah. In 5 seconds, it's here. In another 5 seconds, it's here. In another 5 seconds, in another. A picture like that has a name, a motion diagram. It's very convenient to describe what might be happening. For example, if I look at this picture, I can extract a very important information. We don't have to know physics. We just have to, well, have experience of driving, for example. What is happening to this object over time? What do you think? Yes? Or speeding up. That's what we use usually. It's speeding up. It travels faster and faster and faster. We call it accelerated. So that's why, well, in real life we can't turn time back, but here we could. In that case, if we roll it back, it would be slowing down. Now, next step. We want to see a continuous motion. So to do that, we just connect all the locations by a straight line. Well, in this situation, it's straight, but it could have been curved. A line like that, we call it a path, or a scientific name, a trajectory. And then what can we do? Depending on the trajectory, we can classify all possible motions. A one-dimensional motion is when trajectory is a straight line. It doesn't have to be a horizontal line. It just has to be a straight line. Horizontal, one-dimensional motion. Vertical, one-dimensional motion. Or inclined, one-dimensional motion. When motion is happening like this, when it requires two rulers to measure the location, we call it a two-dimensional. Well, we don't study three-dimensional motion in this course, so all we need is to talk about is one-dimensional motion and a two-dimensional motion. So yesterday we actually saw this is a two-dimensional motion. This is a two-dimensional motion. But this, well, it takes practice. One-dimensional motion. And of course, we need to make a transition from what we see, what we draw, to numbers. There are many ways to do that. First of all, we can use a chart or a table. Yeah? First column shows different times. Second column shows different locations. Well, to get those data, we have to add an additional element. We need a ruler or a measure tape, but a scientific name for this kind of line is the axis. So for example, here, this is a copy of a setup you're going to be using today or tomorrow in a lab. This yellow tape represents the x-axis. Well, it doesn't have to be x, any letter works, but from historical reasons, horizontal axis is called x, vertical is called y or z. And again, technically we don't have to point it to the right. But again, it's a kind of general agreement. Always point horizontal axis to the right. It makes things easier. Everybody is on the same page. Now, every ruler has that what we call origin, 0. So we can choose it again anywhere, for example, at the location of this tree. In that case, locations to the left to 0, described by negative numbers. Locations to the right to 0, described by positive numbers. And those numbers have name, coordinates. So we can apply a ruler and measure these numbers, and write them down. That gives very visible information which can be used further to plot a graph. So the graph is not a physical object, it's a mathematical object. We know different graphs from mathematics, linear, parabolic, circular, etc., etc. Well, in this particular example, numbers chosen to make this a quadratic function, parabola. How do we plot a graph? Just quick review. Well, first number represents the number corresponding to the horizontal axis, but in this situation, this is an abstract axis, not the actual ruler. The actual ruler, we can see, it's the x-axis. This is the abstract line in our mind, which represents time. And at this time, the location of the x-coordinate was equal to 1, well, 1 meter, so 1. The cross-section of these two numbers gives the first point, but this point, again, is not the location of an actual object. That's an abstract mathematical point. Then we go to 5 seconds. 5, 61. Let's assume 61. Intersection gives the second point. 10, 2, 21, etc., etc. And then we connect all those points That gives a graph. Why is it a good thing to have a graph? Because we can make a next step. We have means which allow us to write an equation. And, well, when we have a graph, we already can make additional predictions. For example, I can ask you, if it's not 5 or 10, if it's like 7 seconds, what was the location of that object at t equals 7? Well, we can use this graph and read the number here. But the graph may not be very accurate. An equation gives the answer with more accuracy. To calculate the x-coordinate of that object at t equals 7, all I need to do is just replace t here and here with a number 7. Now, how do I get an equation from a graph? Well, it was really, really hard to do hundreds of years ago. Nowadays, it's just like that. For example, here, wrong keyboard. Here, I have a track, a moving object. Oops. All right. Sabotage. This device has a name, the ultrasound motion sensor. You know what ultrasound is. Yeah, it's a set of pulses which we cannot hear. Those pulses travel away from the sensor, then like echo, they bounce back, get reflected of the object. And there's another device, electronic device, which analyzes that information and transfer it to a computer using USB connector. And of course, we need a special software like this. Actually, let's just start again. So on a desktop, it looks like this, icon or like this. It's called Logger Pro. You start it, connect. Okay. If you hear it, that means everything is connected, everything is working, but I really, really don't like listening to this clicking sound all the time, so I kill it. Now I can start collecting data. I can, well, this experiment is set to 40 seconds. I can change it to 4 to any time. I can stop it at any time. Come on. Now, what do we see? We see that time changes, but the location doesn't. So how do we call it? Rest. It is at rest. Now, of course, a more interesting case is something like this. Well, the top graph tells us that for a certain time the cart was resting, then it started moving, and now we can actually try to figure out what equation could we use to describe the motion of this cart during that selected time interval. We call it doing a fit. Yeah, I fit it with a linear function. If you look closely, yeah, the equation looks like x equals m times t plus b. That's a linear function. X represents the instantaneous location, the x-coordinate of this object relative to a certain origin. I didn't set the origin. I could. There is a function to set it somewhere where I want. But we can see now that if we use this equation, we can plug in any value for time, like 1.7, 2.3, and calculate and check that the number will be the same, which is given here. Those are measured, actual measured numbers. Well, for a while, let's try again. Stop. So this part clearly is linear. And that means that this object was traveling exactly same distance every second. This motion has a name, motion with constant velocity. And equations for that motion is given, and in a couple of more slides, we'll talk about it again. But for now, what if motion is more complicated? What if not? What if it's clearly not a linear function? What do we do? One more example. Here, during this time period, it's not a straight line anymore. We can see it. So what's the next natural option? Quadratic. So we can check a quadratic fit. And we can see, we don't care about what's happening outside of this region, but inside this region, I don't really see any difference between the red line and the black line. So quadratic fit works almost perfectly. So this is a quadratic equation, t squared time constant, which we can use now to predict a location of this object anywhere between this time and this time. Or we can use the table. So this is how nowadays we can get equations which describe some type of a motion, and then we can use those equations to answer many, many different questions. Questions like, where was the object at a given time? How much time was it moving? Or how fast? Now, we've talked about positions. Now, to describe how fast it's moving, we have to say something more specific about how to describe the motion. Now we have to add to our list of definitions several more definitions. First of all, we know what a trajectory is. Yeah. So, for example, if this, I don't know, ghost flying along this path, along this trajectory to get to the treasure chest, the distance traveled by this ghost will be equal to, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 13? 8, 9, 10, 11, 12, yeah, 13 blocks. Each block may be 1 meter. If we use a different trajectory, the distance will be different. Distance can be calculated, can be measured. But distance by its meaning cannot be negative. It's the length of the trajectory. Length can't be negative. So we have to keep in mind the difference between a coordinate, like x coordinate, which could be negative or 0 or positive, and the distance traveled, which cannot be negative because it's a length. Another definition which we use in everyday life is a displacement. So if we don't care about how did we get from this to that, that's where we use this new object displacement. This is an official definition. It's an arrow which points from a start to finish. So do you see a displacement in this picture? No, you don't. You see different trajectories. But if this is a starting point and this is the finish point, to see the displacement, I actually need to get a ruler and connect these lines, or these dots. But that is not a displacement yet. Yeah. What is missing? I need to add a direction, the arrowhead. Now this red arrow, that's what we call a displacement. And displacement is a tricky word because in real life a displacement also might mean action. This object is being displaced. And very loosely in physics people use this word displacement for the length of that arrow, for the magnitude of it. So when you read and it says find the displacement, it doesn't mean you have to look around, where is that arrow? No. Usually it means you need to calculate the length of that arrow. So tricky sometimes. That's what a displacement is. But an arrow is the everyday word. We don't like using everyday words in physics. So we just rename it. We call it a vector. This is not actually the best official definition of a vector, but it's sufficient for us. A vector is an arrow. So what properties does it have? Well, it has to be straight. It cannot be bent. It has a certain length or magnitude or absolute value, and it has a direction, only one. So now, please go to WebAssign. Locate the question number 2 and tell me, how many vectors do you see in this picture? Now I know that it's tough to be, motionless for an hour and a half. So anytime you want, especially when you need to enter your number, you can just, move, like stand up and physically move, or just stand up and sit down, or just stretch. I don't recommend napping. So let's see. So I gotta resend, go to the summary, and check the question number 2. So we do have a certain distribution, 2, 3, 4, and that's a good thing. That gives us something to talk about. For example, is this a vector? What's wrong with that? Is this a vector? What's wrong with that? So that's usually the best approach to figure out what's what. You check every single detail of a definition, and if you see a contradiction, that's not that thing. That's something else. That's it. So if this is bent, what's wrong with this? Has too many arrows. So that cannot be a vector, that cannot be a vector, that cannot be a vector. So we have to check this. Yep, straight, 1 arrow, straight, 1 arrow, 2 vectors, that's it. What's good about vectors that in principle, any possible motion we can consider as a combination of several displacements. For example, in this situation, if we start here and we end there, this arrow represents the actual total, or people say net displacement. But we can consider this motion as a combination of the displacement down, the displacement to the right, the displacement up, and the displacement to the left. So if we know how to analyze a single vector, we can analyze technically any kind of motion, just break it apart in individual displacements. That's not a WebAssign question, but you have to solve it. What does it mean? It means this. If your answer is 1, well, you can use your left hand, it doesn't really matter. If your answer is 2, this is one option, that's another option, that's the third option. If your answer is like 10, that's the only option you can use. If your answer is 11 or 12, you're screwed. So please, show me your answer. 6? Ah, okay, I see. All right, what's your answer? You can say it. Just one more person, and I'm done. Yeah, thank you. What's your answer? Perfect. It's wrong, but it's a very good answer. Not 5. But in a minute, we'll talk about this. So what do we do? Well, first of all, we have to use the first step of the physical reasoning, visualization. We have to imagine it. And we have to help that by drawing a picture. What objects are involved? Well, the sun, the earth, you, or somewhere else. Of course, it's not a drawing, it's not an art class, so we don't do that. We choose 1 or 2 objects which are important, and we draw a dot. That's it. That's the object. How does it move? Well, to answer that question, now we need to know something about geography. Yeah? East, west, north, south. So 4 meters west. Now, here this guy makes a 90 degrees turn up or down. Down, because it has to go south 3 meters. Now, distance traveled, we have to go back to a definition. Distance traveled is the length of the trajectory. All right. Do we see a trajectory? Yes, we do. This is the trajectory. Now we have to ask a question. How long is this trajectory? That's not a physical question, that's geometry. If we have a shape like that, to get the whole thing, we need to add the length of individual parts. 4 plus 3, 7. That's how it works. The problem is simple, but the strategy is universal. So please now use this strategy to answer this question. And now you may be on something. It's exactly the same situation, it's exactly the same person, it's exactly the same process, but a different question. So this phenomenon, this situation, has different features, yeah? And we can describe what's happening differently. Before, we used physical quantity called displacement, distance. Now we want to use a different physical quantity, which we call displacement. And you see, if you had a similar problem given to you in a textbook, the question would sound, find the displacement. Literally, that would mean find the arrow. But of course, they don't want you to find an arrow. They want you to find the magnitude of that arrow, the length So that's why I write the question as clear as possible. You have to calculate the magnitude of that arrow, which we call displacement. So let's see. So resend. Five is the most popular answer, and 5 is the correct answer, of course. Why? Well, first again, we apply the same strategy, so we have to draw exactly the same picture. 4 meters west, 3 meters south. Do you see a displacement? No. So you need to see the displacement, otherwise you can't find it. And to see the displacement, you have to follow the definition. You have to draw an arrow which connects the start and finish, and which points from the start to the finish, cannot be bent. Well, normally, if we want to calculate something, we assign a letter. For a displacement, people use S or L, or delta S or something. Let's call it S. Now the problem is not physical anymore, mathematics. So our brain starts searching for something similar in the past. How does it look like? Does it look like a circle? No. Does it look like a square? No. Trapezoid? No. How does it look like? Triangle. What kind of a triangle? Right angle triangle or shortly right triangle. So the question, what do we know about right triangles? Please. Pythagorean theorem. When we remember something, write down, we immediately ask a question, can we use it? So let's try. If it works, we use it. If it doesn't work, we start trying to remember something else. So can we use this? Okay, in this situation, this is 4, this is 3, this is S, so 4 squared plus 3 squared equals S squared. S equals square root of 25, 5. That's how it works. Again, a very simple problem, but the universal strategy. Now, we're going to solve similar problems again and again and again. So I have to continue a little bit longer asking you, what else do we know about right triangles? Yes? This is a definition of a right triangle. This angle is always 90. If the triangle doesn't have 90 degrees angle, it's not a right triangle. Acute, obtuse, but not right. What else do we know? Yes? All angles, well, theta, alpha, so theta plus alpha plus 90 must be equal to 180, but that actually is correct for any triangle. For any triangle, the sum of all angles is 180. So for a right triangle, please, something else. Yes? Thank you, exactly. We need to know some tricks. So there's one word which I prefer using when I answer this question. What do we know about right triangles? Everything. Maybe you don't have it partly in your memory, but you can easily Google it. I advise to start preparing your own equation sheet. You will not be able to use it on the exam. For the exam, there's an equation sheet which is prepared and available already. You can look it up online. But for you, for your classwork, for your homework, for your lab work, I advise you to start preparing your own equation sheet, like on the back of your notebook, writing down all important equations so you could find them quickly, not flipping through the pages, So, and this is something which should be a part of your equation sheet. This is what we know about right angle triangles. for any right angle triangle, well, we can always apply Pythagorean theorem, and we can always relate length and angles using this or this or this equation. So this is a blast from the past. Let's just use it for calculating something specific, like reviewing how can we use it. Let's say this is our triangle, 3, 4, 5. We know that if this is 3, this is 4, this is 5. And let's calculate this angle. This table, this chart, gives just examples for some angles. But we will see that this angle is neither 30 nor 60, 45. So what do we do? Well, first we have to redraw the picture. To bendy, has to be straight. That's the most challenging part, if you don't have a ruler or protractor. Now we have to add as much information as available. So the short side equals 3, another side equals 4, and we know already this side is equal 5. This is what we're looking for. That's a Greek letter theta. In physics, in mathematics, people like using Greek letters for angles, alpha, beta, gamma, theta. So now we have to choose what equation to use. And technically, it doesn't matter. So please tell me, what do you want to use, sine, cosine, or tangent? Tangent. So if it doesn't work, it's her fault. Tangent of theta has to be equal to, well, again, that should be opposite over adjacent. It's useful to write it once. Now, opposite to what? Is it opposite to the sun? Opposite means opposite to the angle in this function. So what side in this triangle is opposite to the angle? 3. So hence, tangent of theta should be equal to 3 over, and what side is adjacent? 4. And 3 over 4 is 0.75. Are we done? No, the question is calculate the angle. So far we just found the tangent of that angle. We could try to use the table. So, but this table doesn't have tangent, so we can't use it. Of course, that's what we have to use. What did I do? So every calculator has an inverse function, an inverse tangent, inverse sine, inverse cosine. But every calculator has different combination of buttons to use that function. And you need to know, for your specific calculator, how can you calculate the inverse tangent. On my calculator, and that's on my calculator, I have to use the second function button. Then I have to press tangent button. Then I have to press left of the parenthesis. Then I have to enter 0.75. Then I have to close the parenthesis. Then I have to press enter. And I read the answer. My answer is 36.86989,765. What? Does it have a unit? Yes. And 36 point, what unit should I write here? Well, this is what your calculator tells you. because every calculator has different modes. This calculator, by default, is set to degrees. So this is degrees. Your calculator, by default, might have been set to radians. And in that case, your number will be different. So pay attention to units. So this angle theta is about 37 degrees. Not 30, not 60, 37. What about this angle? Can you tell me now the value of that angle? What's the fastest way? Do we need to use any functions? No. Now we can use that rule. 180 minus 90, well, 90 minus 37, 53. 53 degrees. So 30, 60, 90 triangle is the right triangle, but 3, 4, 5 triangle is not 30, 60, 90. It's a different right triangle. All right, so that's not new information. That's not a new information. That's a review. That's what we call a displacement. That's what we call a distance. And something, when something is being displaced, very often we need to know how fast it is happening. So to answer that question, of course, now we can ask, how fast does distance change? Or how fast does displacement change? And depending on the answer, of course, we get 2 new physical quantities. So these are definitions. If we know the total distance traveled, and we divide that number by the elapsed time, the time for traveling, the result has a name, distance over time, the result has a name, average speed. Now, we just said distance, any distance, it's a length. So it cannot be negative. Time is never negative. So what does it tell us about speed? It's never negative. That's what you read on your speedometer when you drive. It's always positive. It measures your speed. Well, speedometer measures your instantaneous speed here and now, not average. Average speed is over the whole trip. But if instead of distance we use a displacement, which is a vector, and we divide it by time, in that case, the result has a name, average velocity. Well, we don't use words, of course. We use equations. So for every physical variable, we assign a letter. A standard letter for average velocity is V. Displacement, R or delta R. Time, T or delta T. Speed, just V. Length is L or S. To show the difference between a number and a vector, when we write our notes, we use those arrows on the top. So this arrow represents a word, a vector. If you don't see an arrow, that's just a number. But contemporary textbooks do not use arrows anymore. So sometimes you may be confused. In a textbook, usually a number like this, a letter like this, represents a number. But if it's a bold font, very, very thick, that is usually a vector. For us, that is the same as this notation, a letter with an arrow. So symbolism is important because it's a part of the language we need to be able to read and understand. Well, I'm going to ask you one more question, maybe more later, but so far this one. Now it's not you walking. It's a fly flying. But it's trained. It knows exactly how to fly. So first, it flies west. And it took 6 seconds for this fly to travel 4 meters west. Then it makes a turn and travels 3 meters south, and it took 4 more seconds. So now, using this information and these definitions, you should calculate and enter what was the magnitude of the average velocity of that fly over the whole trip. Of course, if you have a question, if you think information may be missing, you can ask. But in this situation, I don't think any information is missing. And of course, I advise you to draw a little picture. You have a question? No? And using that picture and using these definitions, calculate, well, what we need to calculate. And I also advise you to form some bonds with your fellow students, form groups, and maybe, if you're not sure, to discuss your thoughts. Wherever. So 4 meters west, and it took 6 seconds. Now, 3 meters south. This part actually no different at all from 2 previous situations. We only have one additional information about time. 4 more seconds. Now, before moving any further so far, what else could we find out? Well, for example, we could calculate the average speed on its way west only. Yeah. It would be 4 over 6. We could calculate the average speed. So only during the second part of the motion. Average speed. I'm just giving you time to finish your work, sir. It would be distance over time, 3 over 4 meters per second. We could be calculating average speed for the whole trip. Yeah. How would we do that? Is it 4 over 6 plus 3 over 4? Yes or no? What do you say? No, that is a wrong way, because that doesn't follow the definition. Wrong. Don't do that anymore. What would be the right way to do it? Well, the average speed should be equal to distance over time. What is the total distance? 4 plus 3. What is the total time? 6 plus 4, so 0.7. Does it answer this question? No. So what do we do? Keep working. First, if it's about average velocity, we have to apply literally a definition of average velocity. Average velocity equals displacement over time. So displacement, we said that word, so we have to do something about it. We have to see it, we have to find it. Do we see a displacement? No. We need it, but we don't have it. What do we do? Well, you need money, but you don't have it. What do you do? Make it work. Yeah, we have to add our actions. So now we can see the displacement. Now, if we want to calculate the magnitude in mathematics is being described by this symbol absolute value. So the magnitude should be equal to, and now we know the magnitude of this is 5, right? But the total time is still 10. So 0.5 meters per second. Again, it's a very simple problem, but it demonstrates how we need to use a general strategy which allows to solve any kind of problems. Any questions? Well, as we said, we're going to talk about two-dimensional motion and one-dimensional motion, but technically any two-dimensional motion is a combination of two one-dimensional motions. So first we need to study one-dimensional motion, and then we can apply that information twice, and we will be able to analyze any two-dimensional motion. One-dimensional motion, as we know by definition, is the motion when trajectory is a straight line. Maybe horizontal, maybe vertical, maybe something else, but it has to be a straight line. So what do we do first? We adding the x-axis. We choose the origin, show in which direction coordinates are positive, in which direction coordinates are negative, and oops. Like let's say this track with a cart on it, and the cart is traveling horizontally, maybe to the right, maybe to the left. So what do? We draw the axis. We choose the positive direction to the right. We choose the origin where? Anywhere. Let's say here. And now, relative to this axis, when the cart is moving, we can read different values as we did. Let's say it was here initially. Then we can draw a motion diagram. In 5 seconds, it's here. In 5 more seconds, it's here. So let's say this is the final coordinate. From start to finish. How do we call this arrow? This particular arrow? Displacement. This is a displacement of this object. Well, in this situation, it points to the right. What is the magnitude, well, of this displacement? Well, it is equal to this difference. But if I ask you to calculate this difference without absolute value, this number might be positive or negative. It depends on the direction of the motion, right? If the object travels to the right, so this difference is positive. We're subtracting small number from a large number. But if we start moving this cart backward, this difference will be negative. So what is a relationship between this number, the magnitude, and this number? Well, unfortunately, every textbook calls this also displacement. So that's another meaning of the same word. So we have to read carefully. But there's another more convenient name. We call it a component. So this letter S represents a vector, a displacement. But this vector might point to the right, or it might point to the left. And when it points to the right, we say the x component of this vector, which is equal to this difference, well, positive. But let's say a cart, an object, same axis, but the motion diagram is backward. So that's x initial, velocity points to the left, that is x final. This is 0. Delta x will be equal to still final minus initial, but now it will be less than 0, negative. Do you see a displacement? Not yet, but we can easily add it. It should point from start to finish. And now we can see that this arrow points to the left, and we say the x component of this arrow is negative. This is terminology. So an arrow is an arrow. It's an object with a pointer. It might point in any direction. But we can assign a number to this arrow. One number assigned to this arrow is positive. We call it length or magnitude. Second number might be positive or negative, and we call it a component. And second number is positive for an arrow directed to the right, but is negative for an arrow directed to the left. Or you can just apply a straightforward definition of horizontal or one-dimensional displacement, final coordinate minus initial, and the result will be automatically correct. Any questions? Again, that's a terminology mostly. And of course, all definitions we used 5 minutes ago remain applicable. So still, displacement over time gives average velocity, distance traveled over time, average speed. But now, this technically is not a vector, it's a number. It is a positive number if the displacement is positive, if the total displacement of the object to the right, but it will be negative if the total displacement is to the left. This number will be negative. But again, speed is never negative. Still, you're dividing positive distance over positive time. So, just an example. Let's do this problem together. You should start in your notebook, and I'm going to do it here. Same fly, but now it flies slightly differently. So, it starts here for 6 seconds. Bless you. 6 seconds, it flies 4 meters west, but then it makes a turn, U-turn, and flies 4 seconds, 3 meters. As we said before, any motion is just a combination of several individual displacements. In this situation, we have 2 individual displacements, 4 meters left and then 3 meters right. So the total final or net displacement is this arrow, blue one. Now, if we want to do numbers, we have to add the x-axis, because without x-axis, we don't have any numbers. And we always point it to the right. Now we have to select the location of the 0 of the origin. Where can we choose the origin? What is one word which answers this question? Where? Where can we choose the origin? Anywhere. So now I want to ask you, where do you want to choose the origin? Why not? Technically, it absolutely doesn't matter. But normally we choose it at the initial or final positions or the most left position. Three most common choices. All right, if this is 0, that will be the x, well, so that will be our initial coordinate. X initial equals 0 because we set it to 0. This is not the final. This is, we can call it west. Yeah. What number should I write for the x west? What number should I write for x west? It's a number line. Everything to the left to 0 must be negative. So this distance from this point to this point is 4, but the x-coordinate of that point must be negative 4. All right. This point represents the final location. So what number should I write for the final x? First of all, do you think it's going to be positive or negative? It's still to the left to 0, so it still has to be negative. All right, negative. Negative what? 1. And to do that, we don't do physics, we do geometry. The length of this, well, segment is 4. The length of this is 3. So what's left is the magnitude of s, but the coordinate is negative. All right. What can we do now? Well, everything. Yeah. Average velocity. Okay. Average velocity equals delta x over delta t, which means x final minus x initial divided by total time. Please, what should I write for the total time? 6 plus 4. So negative 1 over 10, negative 0.1 meter per second. Why is it negative? Because essentially it moved to the left. It was moving a little bit to the right, but still the total displacement still is to the left. So the magnitude of it, the magnitude will be, of course, a positive number, 0.1 meters per second. Any questions? All right. It went longer than I thought. You know, last year, the first day of the semester was Monday. So today, so this time I have to compress everything, and still it's not compressed enough. I want to go to this. It should help you to get prepared for the lab. So everybody who will be doing the lab today will be suffering a lot. But I will finish this topic tomorrow, so people who will be doing this lab tomorrow will be happy. I forgot to bring something to tilt it. So let's say we tilt it. Clearly, if we let it, too much friction. This is the difference between the theory and practice. In theory, everything works. In practice, you have to make it work. All right. Okay, better. So clearly, when it's moving down the incline, it's moving faster and faster and faster. So we call it speeding up. But we can use exactly the same setup to make it move slower and slower and slower. To do that, we just have to push it toward the sensor. And in both situations, when velocity changes, we still can apply the same definition for average velocity, same definition for average speed, but also we need a variable which describes how fast velocity changes. And to do that, we're adding one more physical quantity. We call it acceleration. Well, in this situation, just average acceleration. This is an official definition. So if we need to calculate the average acceleration, we need to know the velocity of this object at one location, and we need to know the velocity of the same object at another location. We need to subtract these two numbers, and we need to divide by the time it traveled from the first location to the second. That's what it is. How can we get that? Well, that's where we use our software again. So the motion of the cart in this graph happening within this shaded interval. I selected it. I just hold the left button and just drag the cursor. And well, well, first of all, you know how to make a fit. You can make a fit, quadratic fit here, or a linear fit here. But if you want to calculate something like average acceleration or average velocity, the most convenient approach is using that table, because we can read exactly the value for location or velocity at any instant. So for example, here, so please write it down, because I can't use this screen. At t equals 0.4, velocity was 0.016. And at t equals 1.2, velocity was 0.017. So if we want to calculate the average acceleration of this object, we just have to subtract two numbers. Yeah, 0.017 minus, what did it say? 0.06 divided by 1.2 minus 0.4. But the most important part is that we can choose any 2 points and calculate the average acceleration in this case again and again and again. And we will get exactly the same number. So for this pair of locations, we get wherever we get, what, anybody? You don't know? Well, doesn't matter. You take this pair of locations, calculate the average acceleration, and you get the same number, and again and again. In a case like that, we don't really call it average anymore. We just call it acceleration. And the motion like that has a name, the motion with the constant acceleration. Now, as we saw already, what happened here? What happened? what just happened? So as we saw already, for any situation like that, here, the equation always was quadratic. So this equation, which describes the location of a cart, has a name. We call it the motion equation, the equation of the motion. It's quadratic, and we can extract that equation from the graph. It always has three terms, just a number, a term with just the time to the first power, and the term with the time squared. But that only for x, for the position. This is a mathematical expression. In physics, we rearrange it. We write it differently. In physics, we don't use capital A, capital B, and capital C. In physics, we use initial value, which is just a constant, same as C. This is an equivalent of capital B. And that represents initial velocity of this cart. If we release it from rest, it's 0. If we hit it, it's not 0. The trickiest part is here. This coefficient, in physics, we break in half. So this is how we write it. Why? Because if you write the motion equation like this, with a half, the equation for velocity automatically has only this letter A. And that is what acceleration is for this situation. Those average accelerations you've been calculating again and again, getting exactly the same number. And to finish, I want to do one example. So, motion equation. So, what information can we extract from it? First of all, we need to rearrange it. So, x initial plus initial velocity time plus 1/2 acceleration time squared. This equation should be an equivalent of this. 6 plus 24 times time minus 6 time squared. A letter x and the letter t, they both represent running variables. All other symbols represent some constants. For example, here, clearly, in this particular example, the initial location of this object should be equal to 6. Here, in this particular example, clearly, the initial velocity should be equal to 24. And finally, the trickiest part is here. We need to divide this term to separate the variable time squared, from everything else. And if we do it correctly, that's what we see, right? 1/2 times acceleration should be equal to -6. This is where people, that means I have left 1 more minute. This is where people might make a mistake, but now we can finish this calculation. -6 times 2, -12. And to measure acceleration, we have to use unit velocity over time, so meter over second over a second, which gives meter per second squared. All right. Thank you. I'm going to pick up from this tomorrow. By now, you should be able to solve like 3 or 4 homework problems at least, and ready more or less for the lab. So. You can take the Correct first. Just give me this. Yeah, that's by hand. Yes.
So, I'm going to miss this. What should I do about that?
I'm not sure your question.
I'm going to miss the lab tomorrow. So,
Tomorrow. Why?
I have to go and graduate.
Okay. I advise you to enter any section you can enter today and do the lab today. Today we have 3 sections. So go into, well, one starts 11, I think. Yeah, 11 to 2:30, 2:30 to 6, 6 to 9:20. So pick one and go in that section.
All right. Sorry, what did you say the third one was? 11 or
11 to 2:30, 2:30 to 6, 6 to 9:20.
all right, and that's in the normal science.
134.
134.
It's across this hallway.
Okay.
Hello. Yes.
I'm registered for the 2:30 to 6 lab. I work from 3 to 8 on Thursdays. Is there any way I can sneak into either the Tuesday, Thursday section or the 11 a.m.
Well,
Wednesday section?
that's not a quick question, so I can't answer now. You should probably wait
Sure, I can wait.
a little longer.
Not a problem.
What is happening here? Yes, I'm listening.
So if I didn't take a class yesterday, the lab, and can I take whatever the lab today section?
All right, that's not a good question. Please give me 5 more minutes and we'll talk outside. Okay? By the way, I asked my department chair if my class listed from 8:30 to 10 Wednesday, so he said 10. I know that, but again, it's not your mess, it's not my mess, so we just have to be patient with each other.
Well, the classes at BU always end 15 minutes before, right? That's the travel time.
Well, the class is listed always according to the time they should begin and should end. In the summer, probably they just didn't do that.
In the summer, they're just probably incompetent.
Well, yeah, but
We have it, so, I mean, you could try to switch up rooms.
I planning on ending every time exactly at 9:50.
Okay, and I'll plan to walk in at 9:52.
Yeah, no problem. I just want to make sure.
So I'm not trying to get in here.
No. I just try and do my best.
Yeah.
All right. Oops. Your mic is in the drawer. Yeah, I'm using my own mic. I'll meet you over there. I just want to go to here.
Oh, my sister.